branched covers of. Oh, sorry, I just got the recording notification. Okay, so the title of this talk is Branched Covers of Twist Spun Knots. Branched covers. So let me ask you a question. Everyone in this Zoom room has thought a lot about classical knots and links. What's the consensus here for like how much have you thought about two-dimensional knots and links in S4? Like at all? A little? A lot? I have no idea. But this is something. Oh, Diani unmuted. Yeah. What's your opinion?
I was just gonna say not a lot, but very interested.
Yeah. So this is something that I think about a lot more than I think about classical knots and links. So when Ali emailed me and said that the theme was branched covers of knots and links or knots and link exteriors, my mind naturally went to what are some recent things I've done in the two-dimensional knot in S4 case. So I hope that that still counts as interesting. That's what I'm going to talk about. Oh yeah, Anthony says little, little. That's good. Okay. I want to tell you something about branched covers of two-dimensional knots in S4. And in order to do that, we at least have to agree that two-dimensional knots in S4 exist, but more than in the theoretical sense. I need us to actually have some examples of these things so that I can tell you a theorem statement. Okay, so the first part of the talk today is going to be going over what is the most classical construction of knotted two spheres in S4. And in this talk, everything is going to be smooth. It's not super important what the category is, but if I don't say, I probably mean smooth. Okay. So the most classical version of a knotted two-sphere in S4 is what's called a spun knot. This is due to Artin. I forgot to check the decade, but old, I don't know, 1940s, something like that. So here is the data that we need to put. We need to specify a classical knot. So this is determined by a knot K in S3, but our spun knot is going to be a knot S2 in S4. Okay. So here's a schematic for what a spun knot looks like. The idea is that we want to construct our spun knot by first decomposing S4 into simpler pieces. S4 is inherently bad because it's four-dimensional. Four-dimensional is bad, I guess. So what we could do is cut S4 into two smaller dimensional pieces, at least at the level of homotopy. So we might notice that S4, well, okay, something you might immediately notice is it's the boundary of B5. That's nice. That seems trivial, but of course that means that it's the boundary of a B3 cross B2. So then Leibniz rule, we get S2 cross B2 union B3 cross S1. So the four-sphere splits as a union of a thickened two-sphere and a thickened circle. Okay, so these are going to be our two basic pieces in our decomposition. This is a general fact. It's like a classic exercise in any textbook about low-dimensional topology that you can write spheres as unions of neighborhoods of low-dimensional spheres. So I bet you've seen some version of that before. So here is going to be our spun knot. I'm going to use the notation, and this is not going to make sense at first. There's this like decoration at the front, tau 0, rho 0. We don't know what that means right now. And the only input is k. So this is our input. Okay, and I'm going to construct a sphere. I'm going to write this by specifying its intersection with each of these two fundamental pieces. So really, I should push this a little bit over to the side and write it as a pair. S4, along with the sphere, is a union of some piece that's inside the S2 cross B2 and some piece that's inside the B3 cross S1. Okay. And at the same time that I'm splitting S4, I also see here that I'm going to have a decomposition of S2 into two pieces. So I might notice the same thing about S2, but here I can just draw it because you'll all know that this is true. S2 splits as a union of, S0 cross B2 union B1 cross S1. It's exactly this decomposition, but down two dimensions. So this is kind of obvious because we can just see the two sphere, right? S2, I can write it as a union of two disks plus an annulus. Okay, so I'm going to use exactly that decomposition here to construct my spun knot. In this piece, I'm going to describe two particular disks in S0 cross D2, B2. And in the B3 cross S1, I'm going to construct an interesting annulus. And I just need to make sure that the boundaries of these two disks and the annulus match up so that their union is perfectly a two-sphere. Okay, so let's go ahead and do that. I'm going to start with the B3 cross S1 because that's the interesting part, and that's where we're actually going to make use of our classical knot in S3. So if we have a classical knot in S3, we might as well think of it as, and this is the notation I'm going to use, a tangle inside of B3. So I'm using this like interior symbol just to indicate that I've like punctured my knot and made it into a tangle. So this is a one-stranded tangle. Okay, so I'm going to think of B3 cross S1 as B3 cross I with the ends glued together. Okay, so this is my B3 cross S1. So here's each a B3 factor that I've drawn at both ends, and this looks like an interval, but it's really an S1, right? Because I glued the ends. And then I have this particular tangle inside of B3. I'm going to take that tangle inside of this first copy of B3, and I'm just going to take that cross S1. So in this picture, it's going to look like tangle cross the interval, but then the ends are glued together, okay? So abstractly, what is the surface? It's an annulus, because it's an arc, the tangle, cross S1. So this is an annulus. So maybe I'll call this A, and then it depends on my classical knot K. So I'll call it AK, and that's the piece that I'm going to put here. I've done my color coding backwards. I hope that's okay. But so I'll have this annulus that depended on my knot. But even though the annulus depended on my knot, the boundary of it is really uninteresting. The boundary of this annulus is just the north and south pole of the three ball cross S1. It doesn't matter what the actual classical knot is. I just get the same boundary. So here I'm going to specify two disks who have that same boundary. I'm going to take literally those 2 points. Let's give them a name in this picture. I'll call them like N and S for north and south. I've seen that before and I kind of like it. So here I'm going to take uh, the north and south pole cross B2. So that sits inside of S2 cross D2, or S2 cross B2. It's just literally 2 points in the two-sphere cross B2, sits there nicely as a product. And of course, the boundary is, again, the north and south pole cross S1. So this is two disks that exactly match up with this annulus to make one two-sphere. So this is a two-sphere. It's called the spun knot. We can actually visualize these pretty easily. Easy with quotation marks. It's easy once you've done it a few times. It is easy, but so here's how I like to imagine these things. I like to imagine S4 first of all as S3 because that's hard. So everything is just going to be down one dimension. So this line is supposed to represent a two-sphere. It's the two-sphere S2 cross 0 inside of S2 cross B2. It looks like a line, but it's really two-dimensional, and it's really compact. Everything's compactified. And then I have these B3 cross S1, and in this picture, that's going to look like the fibration of this unknot complement. Okay, so my different B3 cross circular angles will look like pages coming off. So this is like B3 cross 0. Maybe this is, B3 cross pi over 2, and so on, sort of a circle's worth of them. I have a weird selection of colors in my menu. I don't know why I did that. Okay, so those are the different B3 cross S1s in this decomposition. So imagining this is only as hard as imagining the fact that the unknot complement is fibered. I bet you've all done that before. So now I can construct this two-sphere. Well, inside of each one of these three balls, I was supposed to have this classical tangle. Maybe I'll use a slightly bigger pen. So inside of this first three ball, I have this tangle. And in this drawing, I've drawn it like it has a crossing, but it's really all in this plane. Where there's a crossing, this is not underneath in a visible third dimension. That means that piece is actually deeper in the fourth dimension, which isn't in the picture. Okay, so in this three-dimensional cross section, you should imagine this is really a diagram. It's like a glass pane with a drawing on it, and if I turn it around, I'll see the same crossing. It's not like over and under, it's 4D. So I'm going to take the same crossing, the same like glass pane, and just sweep it around. So I have the exact same tangle in every one of these three balls. So when I get to the red one, I'll have something like this. Okay, so if I took that tangle and I flipped it over, that's exactly the diagram that I would have, right? It's the mirror. And then orange, something in between, and blue. Wow, it's really hard to draw that. Okay, that's pretty good. And they trace out a two sphere. So this is the spun trefoil sitting inside of four-dimensional space. Wherever it looks like it intersects itself, the broken sheet is deeper in the fourth dimension. Okay, so this is a pretty nice family of knots. They're very well studied. Even these are enough to tell us things like there are infinitely many knotted two spheres in S4. We can look at like pi 2 of the complement of these guys is non-trivial. Unlike classical knots, two knots are not aspherical, and even these examples show us that. That's bad. But for the purposes of what I want to tell you today, these are like not interesting enough. I have to soup these up a little bit. Okay, so we're gonna go to a generalization of spun knots. And I'm going to do two generalizations at once for time. And these are going to be the twist roll spun knots. And this is where this notation is really going to make sense. So twist roll spun knots. So before I used this tau and then I wrote 0 and then rho and I wrote 0 and then a classical knot K. So now these things are going to be inputs too. Maybe I won't write a box. Maybe I'll just write a number. So tau m, rho n. So here m and n are going to be integers. Before they were just zeros. And then k is still a classical knot in S3. So in words, I would call this the m twist n roll spun knot of K. It's never been very clear to me if it's the spun knot of K or if it's the spin of K. Like, is it past tense or present tense? Because you're sort of doing the operation now, but the two knot kind of already exists, you know? And I think people are not very consistent about that. But we're going to construct this in exactly the same way, where I'm going to use this decomposition of S4 in two pieces, and I'm going to specify that this particular two knot sits inside of S4 by specifying its intersection with these two pieces. So I'll have the S2 cross B2 piece, and then I'll have the B3 cross S1 piece. Okay. So let's look at first this B3 cross S1 piece, because this is going to be the interesting one, just like before. So here's my same picture of B3 cross S1. But you notice before I said I think if it is B3 cross I with the ends glued together. There's not really a reason for that if I'm literally thinking of something as B3 cross S1, like products are already easy enough. The reason that we might like to think of it like that is I wasn't very careful before when I said glue the ends together. I really have to choose a homeomorphism here. Which seems like it's not that interesting because any two homeomorphisms of the three ball that agree on the boundary are isotopic. Like, it seems like this shouldn't matter. But the thing is that there's going to be this additional structure where I'm constructing an annulus inside of B3 cross S1, and that annulus inside of B3 cross I is going to just be arc cross I, but the actual annulus that I get will strongly depend on the choice of gluing map that I use here. I'm going to specify that F fixes this tangle, and even though F is isotopic to the identity map, it might not be isotopic to the identity map while fixing the tangle, right? So it's not true that we would expect this annulus to necessarily be not cross S1. It might actually be interesting. So for some knots, there might be many choices of interesting homeomorphisms here when you have a knot with a lot of symmetry. But for any knot, there is a two-parameter family that correspond to the twisting and rolling that I can always define. So let me tell you what those are. So we're going to use, for the N twist, N roll spun, I'm going to switch these numbers. For the M twist, N roll spin, we use a specific map. Okay, so this is going to be the map that is supported on a neighborhood of a torus, very close to the knot. So let's zoom in so we can draw this a little bit better. Here's the torus. First, I'm going to take a tube, which is very narrow and follows the path of the knot. Okay, and it doesn't quite make it to the boundary. This is totally in the interior of the ball. So right now this is two boundary components. And then I'm going to cap it off by another tube, an annulus, which is parallel to the boundary of the ball, like this. Okay, so in the language of satellites, it's some kind of swallow follow torus, right? I like followed the tangle and swallowed the boundary. I don't know. And of course, I can always make a torus analogous to this, no matter what tangle I'm using. And this torus, I really want to think of this as S1 cross S1, where the two S1 factors are the meridian of the tangle and the zero-framed longitude of the tangle. So I have the meridian, and then maybe I won't try to draw the whole longitude because that's kind of a mess, but it goes this way. And I'll take the zero-framed one. Okay. So now what I'll do is I'm going to use specifically the gluing map to glue these ends together, where I'm going to write of x is, well, it's just fixed if it's not in a neighborhood of this torus. Neighborhood of this torus, if I call this t. Well, a neighborhood of the torus is parametrized as S1 cross S1 cross I. So when x is in the neighborhood, that means that it's equal to some S1 factor, another S1 factor, and an I factor. So that's our S1 cross I. And what I'm going to output is, well, I'm going to fix that I factor, but I'm going to change these two circular factors. The first one, as t ranges from 0 to 1, I'm going to have the number of twists increased by m. I'm going to go through m twists. So let's have theta plus 2 pi mt. Okay. And then the second angular factor, I'm going to do theta plus, or sorry, psi plus 2 pi nt. Okay. So this is telling me that near the torus, as t increases, I twist all of the points m times around a meridian of the knot and n times around a longitude of the knot. Okay. Now, that map is isotopic to the identity, but not in the knot complement. In order to actually do the isotopy, I'd have to move the knot, reparameterize it, and also twist it, which I'm not allowed to do. Okay, so when I do this, I get just some other annulus. It's not isotopic to the one from before. So maybe I'll call this A, and it depended on M and N. It also depended on my knot K, but I won't write that. But the boundary is totally the same because this map doesn't do anything to the two boundary circles or anywhere on the boundary. So the boundary is still just north and south pole, process one. So I can cap this off with the same two disks as before. I'm going to use, if I call this again, N for north and S for south, the north and south pole across B2. So those two boundaries perfectly match up. Two circles here, and I get a two-sphere sitting inside of S4. And it depended on both of those integers and also the choice of classical knot that I used. So it's quite a bit harder to draw this kind of picture of the twist roll spun knots. One of the reasons that it's quite a bit harder is that when we think about what do surfaces look like when projected to dimension 3, there's more kinds of self-intersections than there are for knot diagrams, right? When we have knot diagrams, we only have double points. For surfaces, when we project down, we actually expect triple points. This particular diagram that I drew doesn't have triple points, but in general, these kind of things are going to have triple points. They're just like hard to draw. That's all I can say. So usually when we manipulate these kinds of objects, we just don't draw these kinds of projection diagrams. It's kind of a novelty for spun knots. Okay, so this is what a twist roll spun knot is. Okay, so it's not obvious right now why we care about this, but I promise we're gonna care about this. So let's come back to that. So I am gonna tell you a theorem about these. So keep it in mind, we know these exist. And before I tell you a theorem, let me tell you some like open problems about surfaces in dimension 4. Okay. So, part 2, what are some open problems? So, one of the main open problems in this field of knot theory, open problems, is does there exist an exotic unknot? And in fact, maybe I shouldn't have said the word exotic. Maybe I should have said it as i.e., is the unknotting conjecture true? That'd be a better phrasing. Is the unknotting conjecture true? Maybe I'll leave it like that instead. So I think this sounds really weird if you're coming from the perspective of being like an actual knot theorist in dimension 3, because you know the unknotting conjecture is true. The unknotting conjecture in dimension 3 is, of course, that if you have a knot in S3 and its fundamental group is cyclic, then that implies that K is the unknot. Okay, so we all know that's true. But in dimension 4, we do not know that that is true. We know it in many cases. So in dimension 4, so first of all, I should tell you what I mean by unknot, right? In dimension 4, an unknot definition, if we have a surface that is oriented, then we define unknot totally analogously to dimension 3. In dimension 3, the knot that is the unknot is the one that bounds the simplest possible thing, right? A disk. So we think if we have an oriented surface, what's the simplest possible thing that it could bound? Well, if it's a sphere, then that's a ball. If it has genus, then it's a handle body. That's the simplest three-manifold I can think of. And of course, that includes balls. Balls are handle bodies. So a surface in S4 is unknotted if it bounds a handle body, a solid of genus G. My grammar is weird here. Sigma is unknotted if it bounds a solid of genus G. So in dimension 4, we actually do not know if the unknotting conjecture is true. So this is unknown. So with some qualifications, when I say it's unknown, I mean smoothly. As you might have thought about before, in dimension 4, there's a really big difference between smooth and topological isotopy, locally flat isotopy. So what we do know in the topological category is a lot, but actually still not entirely the whole thing. We know the case when G equals 0. So two spheres with group Z are topologically unknotted. This is the theorem of Friedman. Late 1980s, early 1990s. And when genus is greater than 2, it's also true, and this is by Conway Powell. I think that's 2020. I'm mixing up papers, but I think that one's 2020. So technically, we actually don't even know this in the topological category for genus 1 and 2. But in the smooth category, we just like don't know anything. Like a very little partial progress, if any. Like I can't even think of anything. With one caveat. Weirdly, we actually understand this much better for non-orientable surfaces, which I feel like goes against intuition, like non-orientable bad, right? You would think so. I mean, maybe this is an example of non-orientable being bad, because for non-orientable surfaces, in fact, the conjecture is false. For non-orientable surfaces, the analog of the unknotting conjecture is false. Let me state this as a theorem. So the theorem is original version. Oh, I spelled theorem wrong. Finishin, Kreck, and Vero. And this was also 1980s. They showed that there exists a non-orientable surface, in fact, an infinite family, embedded in S4, whose fundamental group is not Z because that wouldn't make sense. Alexander duality tells us that we're expecting the first homology to be the same as the second cohomology, so it's going to be Z mod 2. But it is Z mod 2, so pi 1 S4 minus sigma is cyclic. In this case, that means Z mod 2. But Sigma is not smoothly unknotted, which at this point you should interject and be like, well, what does unknotted mean for non-orientable surfaces? Half of them don't even bound anything. So I should tell you what that means. Definition of unknotted. It's actually much easier for non-orientable surfaces because I just have to tell you what an unknotted projective plane is, which I wanted to do anyway, because again, you need to have some examples. And then for higher genus non-orientable surfaces, we just say it's unknotted if it's a connected sum of the unknotted RP2s. So here's an unknotted projective plane. Literally, here's one. This height function is going to be a four-dimensional height function. So every cross section is going to be three-dimensional. I'm going to draw you a movie that will illustrate a projective plane. Okay, so starting at the bottom, I'm going to have a single point. And right above that point, I'll have small circles. See, so this is tracing out a surface that looks like this. Okay. And then as I go up, remember every one of these cross sections is three-dimensional. So I have room to like move this unknot around. Like I could have it twist up on itself like this. That's allowed. And then these 2 points here, which are far apart on the unknot but close together in space, could actually merge. And then split apart the opposite direction. And if I did that, I would again have an unknot, which I could shrink down to a point. And so this traces out a surface. This X cross section in the middle, if you think about that, I always tell people it's like in calculus 3 when you do the quadric surfaces. This is the hyperbolic paraboloid or the saddle. Remember, it has the X cross section in the XY plane. And then like if we do like, Z is equal to X squared minus Y squared. Then in the xz direction, we have positive hyperbolas. So we have like positive parabolas. Oh, sorry. So we have something like this. But in the y direction, we have negative parabolas, right? So we end up getting a surface that sort of goes up one way and down the other way, and that's the saddle shape. So it is a surface. It's just a critical point in a Morse function. Okay. It's an index 1 critical point. So this is a surface whose Euler characteristic is, well, there's one minimum, one index 1 point, and one index 2 point. So 1. So this is a projective plane because everything's connected. And it's almost the smallest possible projective plane. The only problem with that sentence is the word the, because there's actually two choices here. When I constructed this projective plane, I had to choose when I did this, oops, wrong one. When I did this local, basically a Reidemeister 1 move to add a twist going up, I could have done it the opposite sign. So I could have had the other strand be over, and then it all totally works out the same way, and I get another surface inside of S4, which is also a projective plane. And these are actually different from each other. The difference is their normal Euler number. One of them is positive 2, and one of them is negative 2, and I always get it wrong, so I don't ever. So there's two of them. Two of them, and they're just literally defined by this. One of these two. And then in general, if sigma is a connected sum of unknotted RP2s, then we say it's unknotted. Okay, so why is this important? Finnish and Crack and Vero gave examples in the 80s of connect sums of 10 RP2s. Some weird embedding of this kind of surface into S4 that is topologically but not smoothly the unknot. It has fundamental group Z mod 2Z, so embedded in S4. Pi 1 of the complement is Z mod 2, but not smoothly unknotted. They did separately prove that these are topologically unknotted. Okay. And the obstruction that they used is through branched covers. So they looked at the double branched cover of the surfaces that they are considering. In fact, it's kind of backwards logic. It's more like they started out with four manifolds that they already knew were not diffeomorphic to each other, and then they realized them as double branched covers. I think that direction is like a little bit easier. So the nice thing about these standard RP2s is they're so standard and easy to understand that it's easy to understand what their double branch covers are too. So these particular two RP2s, they're double branched covers. So I'm going to use this notation for double branched cover, sigma 2. So one of these guys is like a positive one, and one of these guys is a negative one. Maybe I'll just use P. I don't remember which one is which, so I've just taken a guess. I feel like I've guessed wrong, actually, but that's okay. But one of them is positive and one of them is negative, which has to do with its self-intersection number being positive 2 or negative 2. And in one case, the double-branched cover is CP2 bar, and in the other case, the double-branched cover is CP2. So something nice and standard. So really what they did to make these examples is they found an exotic manifold, or they knew of exotic manifolds. They used four manifold that is homeomorphic but not diffeomorphic to CP2 connect some 9 CP2 bar. In fact, there's an infinite family of these, and these are kind of famous examples. You might have seen these numbers together when looking at theorems, old theorems about exotic four manifolds. So each of these manifolds in their paper, they realize as a double branch cover of a surface. And topologically, they're also double branch covers of a connect sum of one negative RP2 and 9 positive RP2s. And those are the surfaces that are topologically but not smoothly isotopic. Okay, so it's kind of an interesting idea using double branch covers. And that was improved a little bit using the exact same idea over the course of several decades. So that was connect sum of 10. This was improved finishing. 2006 gave connect sum of 6 RP2s. And again, they're this sort of indefinite behavior where topologically it's a connect sum of one negative RP2 and 5 positive RP2s. Okay, it's always like a mixed number. Whereas before here, this was one positive, one negative, and 9 positive. Okay. And then I'm going to put something here in a second. Just at the very end of 2023, maybe early 2024, I forget, there was a paper by Gordon Matic, Ozturk, Stipschitz, very similar, but they improved this a little bit from 6 RP2s to 5. And again, topologically, their surfaces are isotopic to a single negative RP2 and then 4 positive ones. These mixed signs are really important because they're all distinguished by their double branch covers as four manifolds. These simply connected exotic four manifolds. They're diffeomorphic. They're homeomorphic but not diffeomorphic. It's a hard problem to find definite exotic manifolds. So it really makes sense that these have mixed signs. And so one open question was how far down can you decrease the number of these RP2 summands? Another open question was, can you control the signs of these RP2 summands? Can you make definite examples where it's all positive or all negative? So neither of those were clear. And then at the end of 2023, there was this paper by Miyazawa, really cool paper, where he gave exotic just RP2s in S4. So by exotic, these are going to be topologically isotopic to the unknot. I think that for him, I think he says P plus. You can always mirror. It's not like the sign really matters for saying the theorem. But he gives their topologically isotopic to P plus, which means that the complement is cyclic. In fact, it's backwards. The complement is cyclic, and therefore he cites something by Lawson to know that they're topologically isotopic to P plus, but that's fine. But they're not smoothly isotopic, not smoothly unknotted. And again, the obstruction is double branch cover, but in a more interesting way. So Miyazawa, what he does is he has, and I'm going to tell you what the example is because that's important. He has a particular two sphere, RP2 in mind. So let's say we have our RP2 in S4, and we're comparing it to P plus, which is just another RP2 in S4, right? Oh, sorry, in S4. Okay. Um, what we're gonna do is look at the double branch covers again of these four spheres with these surfaces in them. Okay, so maybe I'll draw a circle to indicate this is a manifold now. So this is S4. This is S4. And then I have my twofold double branched cover, where I have sigma of whatever the surface is. And then I have this one. I know what the double branch cover is. It's CP2 bar. Okay. But he actually doesn't study these objects as manifolds. He studies them as manifolds equipped with involutions, just the covering transformations that come from these double branch covers. So here I have one involution. It just interchanges any 2 points that have the same image downstairs. Okay, so that's tau. And of course here I have the covering involution. Actually, maybe you can guess. Like there, it's an involution on CP2 bar. I feel like there's not that many that are natural, right? So, in fact, this one is complex conjugation. Okay, so we're comparing some four manifold, which I know is homeomorphic to CP2, at least. We don't know the smooth structure. And it has an involution on it that came from this covering action. And we're comparing it to CP2 bar with complex conjugation. And what he does is he shows that these two things are not equivalent. So if I'll call this X, X tau is not equivalent to CP2 bar conjugation. But it's not clear from this proof strategy where that inequivalence happens. Like it could be that X is just not CP2 bar. Like that would be cool. Because then that would be an exotic CP2, exotic CP2 bar. That would be an exotic definite manifold, a very small one. That's pretty close to the Poincare conjecture if it's not CP2 bar. Or it could be that X is CP2 bar and it's the involutions themselves that are different. And that's also pretty interesting. It's pretty small exotic behavior, these maps, involutions that are topologically but not smoothly conjugation in CP2. Okay, so the thing that we proved, so I'll tell you the theorem and then we'll see why that example actually applied. Why I did that whole twist spin thing. So here's theorem one. Uh-oh. Sorry, I twisted the lid off my pen. So theorem one. So this is a fact about double branch covers. And this is with Hughes and Kim. I should say that. This is from 2024, I think. Yeah. Okay. So it's a relationship between the double branch covers of the M twist and roll spun knot of K. I'm only going to say a theorem for double branch covers. There's a theorem for higher cyclic covers, but I don't really know. Like, this is kind of the case I think you would care about most naturally for applications. And the first theorem is that there's a periodicity where I can add four twists. Okay, we might say why that's true. In fact, we don't necessarily care about this theorem statement, but there is, and I don't want to say improved, because in some ways it's better, in some ways it's worse. But using basically the same proof, what I can also prove is that, so I'll call this like theorem 2, I guess. If I'm willing to eat the cost of adding an RP2 summand to my two sphere. So that's bad. That's what I mean when in some ways this is worse. I do get a better periodicity result. This is the same thing, diffeomorphic, to the double branched cover of if I add two more twists and then add an RP2 summand. Okay. And so I claim as a corollary of theorem 2, I spelled corollary wrong. Corollary is that Miyazawa's manifolds uh, are diffeomorphic to CP2 bar, and hence there exists exotic involutions on CP2. Okay, so we don't know what the connection is right now between the theorem I just said and the Miyazawa stuff, because you don't know what the Miyazawa examples are. So let me tell you, because it's a little bit surprising. Actually, I'm like, Miyazawa paper is so good. I'm like really annoyed about how simple the examples are, you know? Like, you'd think that would be the hard part is like thinking of them, but they're like right there. It's just he had to invent something. But so his examples, I'll give you one example. He gives an infinite family, but I'll just tell you the first one. So Miyazawa's RP2. It's so simple that it's a connected sum. It's a connected sum of a sphere, so a two sphere, and just the standard unknotted RP2. Okay, so it's gonna be P, and then he was doing, I said P plus. I said P plus, yes. Okay, so that's annoying because it's like if you were trying to construct a projective plane in S4, like the easiest possible thing you could think of would be I'll just take one of the spheres that I already understand and like throw an RP2 onto it. I don't know. And it turns out that that works. It's like amazing. But he has to be really careful about what sphere he uses. And so the sphere that he uses is one of the twist roll spun knots. So in particular, so particularly he's going to take the zero twist, one roll spun of a particular knot, which we'll call J, where J is going to be a pretzel knot. It's the pretzel -237, which if any of you have written papers using some version of Floor homology before studying knots, I bet this knot has come up. It's special. It seems to show up in like every paper. And this is the particular example that he can do. He can show that the double branched cover with involution of this RP2 is non-standard. Okay. In fact, I want to pose a question right here because this is a something that already existed in the literature, but I wasn't aware of until I read his paper. It's really surprising to me that the so one observation that is in his paper is that for this particular two sphere, ignoring the RP2 part, if we take the double branch cover of just this two sphere, then this is a homotopy four sphere. It's a homotopy S4. I mean that in sort of a roundabout way, it follows from his theorem, but it's kind of circular logic. But if we believe that this sphere, when you add on RP2, the double branch cover is just CP2, like that means that at least homeomorphic up to homeomorphism. That means this two sphere, like its double branch cover, isn't contributing anything, right? The double branch cover of a connected sum is a connected sum of the double branch covers. So note, double branch cover of this is just the double branch cover of the sphere part connects some CP2 bar, and the whole thing is homeomorphic to CP2 bar. So this double branch cover is a homotopy four sphere, which means it's homeomorphic to the four sphere by Friedman. I do not know if this is standard, and I really like this as a potential counterexample to the Poincare conjecture, because I feel like one of our biggest problems with Poincare conjecture potential counterexamples is they all come in infinite families, and don't you think that's kind of like reaching a little too high? Like if you're gonna disprove it, you're gonna find like an infinite number. I think just one. I'd be happy with just one. So this is one that comes by itself, you know, which I feel like makes it more likely. Which is I'm not saying like I think this is exotic or anything, but it's pretty interesting. I don't know. Okay. So that's fine. So let me tell you some other facts about this particular knot because it really shows up in a lot of papers as examples. So this particular knot, the pretzel knot, -237, came up in an older paper by Fintuschel and Stern. I forgot to check the year that this is from. It's probably, I have no idea. It's the 90s, maybe. Does that make sense? I don't know. But Fintuschel and Stern have this cool paper about interesting ways of constructing lens spaces by Dane surgery. So just like interesting lens space surgeries. The title is like not exactly that, but I feel like it is close to that. So they have a paper that's called something like this. And this knot is one of my favorite examples, where they show that the pretzel knot, P minus 237, if you do either 18 or 19 Dane surgery, then you get a lens base. I really like it as an example because the proof is like, here's a surgery diagram, just sort of check. I like that kind of argument, so that's kind of fun. So why would we care about this? Well, here's another fact about the twist roll spun knots. So if we have a twist roll spun knot with a non-zero number of twists, it's always fibered. So tau m rho n of k is fibered as long as m is not zero. And this is an observation in the papers that introduced twist spun knots, which I realized I forgot to attribute them. These are constructed by Zeeman for just twisting. And then rolling is an older idea, but I really like the exposition and details of Litherland. So these are observations of both of them that these knots are fibered. And you can describe the fibers really explicitly. The fibers are themselves branched covers, which is another fact you might have seen at least in the no rolls twist spun cases. That's something that people I think are a little bit more aware of. The fibers are M-fold branched covers of and am I gonna get this direction right? I think I am. I think it's cool. M over N surgery? Yeah. N over M. No. M over N surgery. Yeah, there we go. M and N sound the same, so in my head they're like it's hard to get their order right. It's okay. Okay. And when I say branched cover, I'm being a little bit imprecise. Like, as you know, branched covers come in more than just the cyclic variety. Um, so these are going to be branched covers, but the degree is going to be or so then I say degree, the degree of branching is going to depend on the GCD of M and N. In particular, if they're coprime, then it's just a regular cover. The branching is like degree 1, so no branching. Okay. Um, so keep that in mind. We have this fact, this particular knot, okay, whatever it is, it's 18 surgery is a lens base. It's a lens knot like 18, it's either 5 or 7. It's 5. Okay. So let's apply this observation about fibering. Okay, so this tells me that if I take the tau 18 roll 1 spin knot of J, this is fibered. And the fiber is the 18-fold cover of 18 surgery on J. And there's no branching because if there's coprime, the numbers are coprime, and 18 and 1 are coprime, then there's no branching. Well, okay, so if you have even 18 lens base, you take an 18 full cover, that's S3. So the fiber is S3. That's the closed. The closed fiber is S3. So it has two sphere boundary. It's actually B3. So this is actually the unknotted sphere. And this appeared in a paper by Teragaito. Okay, so let's put all these things together. We have this theorem about branched covers. So I'm going to use the theorem 2 version. Let me just copy this. Okay, so this tells us that in this particular case, the double branched cover and for Miyazawa, we're looking at tau 0, rho 1 of this particular knot J, connexum P plus. Well, I can add any even number of twists here. So I could change this to this 18 twist and 1 roll spun of J. So that's tau 18, 1 roll of J. Connexum P plus. This is an unknotted sphere. Connect some with it doesn't do anything. So I just get back to P plus. And that double branch cover is just standard CP2 bar. So the double branched cover of the RP2 that he considers really is the standard CP2 or CP2R. It's the involution itself that's exotic. Okay. And so coming back to this question about is this a homotopy force sphere, I want to point out something so annoying. So we have this theorem. Let's look at theorem 1 statement. And let's see what this tells us. Okay, so this is no RP2s. This is just the actual 2 sphere. So remember, I have this question. So question is sigma 2 double branch cover of the 0 twist 1 roll spun of that particular pretzel knot diffeomorphic to S4? We don't know. And what does this theorem tell us? Absolutely nothing. Because if I look at tau 0 row 1 of J, this is what I want to know. What I do know is that the 18 twist row 1 of J, that's diffeomorphic to S4 because that 2 knot is the unknot and the unknot double branch cover is S4. And the really annoying thing is that 18 is 2 mod 4. So I don't know how to deal with that. So that's again, I feel like it makes the example even more compelling. And I've just about used up the time. It's like on the hour, so I think I'm just gonna leave you with this open question about double branch covers.
Okay, let's thanks Professor Miller for the great talk. Is there any questions? All right, thank you all for coming. It's really nice to see Maggie again after so many years.
Oh yeah, thanks for having me. It was nice. Yeah, I've maybe eventually I'll come to one of the knots in Washington.